Today, for our plenary, it's a great pleasure to have here Benjamin Doyon. So Ben is professor in theoretical physics at King's College, where he's been since 2010. Before 2010, he has held a position at Durham and in Oxford, and his research interests are quite wide and cover, among others, quantum entanglement, conformal field theory, and of course, generalized hydrodynamics, which I guess is the topic of his talk today. So his talk is going to be about from soliton gases to quantum gases, the hydrodynamics of integrable systems. And Ben, the stage is all yours.
Thank you. So it's really a pleasure to be here to give this talk. And yeah, so this is going to be about generalized hydrodynamics. I wanted to make a talk which kind of connects a bit with what I think a lot of people know here, which is the idea of soliton gases. Now, I'm not an expert in soliton gas. I am learning. I'm now kind of discussing with Galen Dale and Thibaut Bonnemet about these things and learning. But hopefully, I can make connections. I'm more expert in the quantum gases than the hydrodynamics of quantum gases. But the point here is to kind of make the connection between these things and kind of display the common features and the common ideas. So let me start. I mean, the underlying idea behind all of that is the question of emergence. This is the idea that I find extremely interesting and very powerful. And the idea here is that if you have a microscopic model, a dynamical system, whatever it is, which with a lot of degrees of freedom, which can be very complicated to describe, you want to find simpler laws that describe what happened at large scales. I mean, the typical example is, the air or any gas, which is a huge amount of trajectories of molecules, which is kind of unthinkable to describe, but you have simpler equations, which are the equation of hydrodynamics. That's the idea behind what I'm going to explain now. Now, I'm going to discuss different models with the point of going from soliton gases to quantum gases. And the typical example of soliton gas is the gas of solitons of the KdV equation. So KdV equation can be used in various physical applications, but in particular to describe shallow water waves. And there's a lot of expression on KdV equation in this virtual room. So here's the KdV equation, but there are different. So KdV equation, of course, is an integrable field theory. It's a field in two-dimensional space-time, which is integrable. There are different integrable field theories, of course, that one can consider. Here's another example, the Singe-Gordon classical Hamiltonian. Now, here is described by two canonically conjugate field phi and pi, and it's just a relativistically invariant classical field theory, which turns out also to be integrable. And similar techniques can be used for these two field theory. And here's another type of model, which is also integrable, but which is a very different type. It's not a field theory, it's not hydrodynamic equation. It is a gas of particles. And here the particles are relatively simple. They just move left and right in a free fashion, except when they collide with each other, where they exchange their momenta. And the only thing that's special about that is that these particles have a finite length. This is called the hard rod gas or the Tonks gas. It's been studied for quite a long time in the context of statistical mechanics, in particular in the context of understanding hydrodynamics. Okay. So these are three rather different models, and here's a fourth model, also very different. It's a bit like the hard rod gas. It's a gas of particles, but this time it's quantum gas. This is the Lieb-Liniger model, where the quantum gas, the particles in the quantum gas interact with the delta function interaction. It turns out that this is an extremely good model to describe experiments on ultra-cold atomic gases, where in experiments by various techniques, you take rubidium atoms, you bring them to extremely low temperature, and you confine them either with laser or with magnetic field to effectively one-dimensional space. And it turns out that this Hamiltonian is a good description of what of this experimental setup. So atoms essentially move in one dimension and interact essentially with the delta function interaction. And this is also integrable. So these are four different models, very different models, three classical one and one quantum one, two field theory and two kind of models of gases of particles. And what I want to say is that there's a lot of things that we can say about this model, which all fall within a common framework. So what we want to look at this model is non-equilibrium behavior, motion at large scales, and there is a single common framework, in fact, a single equation that can describe what's happening in these four very different models. And I want to get to that. It's generalized hydrodynamics. And before I get into that, let me just tell you a bit about the kind of questions that we may ask. Okay? So we've seen already a few talks about soliton gases, even the talks in the morning. So here you think about, say, a configuration of the KdV field, which is random in some way, but which is constructed perhaps by inverse scattering method as a, say, a large density of solitons. So you know how to put solitons in within this configuration by using the scattering method, and you can imagine that you put a lot of solitons so that there's effectively a high density or a finite density of soliton per unit length. And so the field will look relatively random. In fact, this was called integrable turbulence by Zakharov, I think, quite early on in the 70s, yeah. And you can think of this integrable turbulence, in fact, as being some fluctuating field. And you may think of the fluctuating field to have different statistics, say, on the left and on the right. So for instance, think about two soliton gas kind of colliding with each other and then interacting with each other. Okay? But really, this is like a field of KdV, and you want to know what happened when you time evolve this using the KdV equation. Okay? So this is the idea of soliton gas. Now I should say that this is not the only way of making a random configuration of KdV field. There are other ways in principle than putting soliton gas, using gas of purely solitons. There was a talk this morning, in fact, where one looked at influence of a radiation wave, essentially, but you can restrict yourself to the gas of soliton if you wish, and that's perfectly fine. And then we want to know the time evolution of this thing. Okay, so there are certain equations for that, which I think we have seen in some of the talks before. But there are other ways of formulating the problem. Here, let's take the example of the Sinch-Gordon model. Now, the Sinch-Gordon model also admits a lot of various structures, solitons and radiation. But instead of thinking about solitons, why not think about a standard kind of Gibbs measure for this classical field theory, which has a Hamiltonian density. And here, for instance, in this example, I'm dividing the system into two halves, a bit like I was describing now. And one half, I put the system in some temperature, say inverse temperature beta left, and the other half, I put the system in some temperature beta right. What I mean here is that I have a random initial state, which is a statistical distribution of configuration, of field configuration. So I integrate over phi and pi with this measure. So that's my canonical measure for temperature, different temperature on the left and on the right. And then I want to evolve that in time and calculate some evolved observable. For instance, this is a typical observable that you would calculate in the Sinch-Gordon theory, e to the alpha phi. So phi is the fundamental field of Sinch-Gordon. And you evolve that in time with the Sinch-Gordon equation. Now, this is a highly non-trivial problem. And until recently, nobody knew how to calculate, even with the methods of integrability, inverse scattering methods and all that, nobody knew how to evaluate this as function of xt. In fact, still, it's very complicated to evaluate as function of xt. But what is possible to do, so the question here is the problem of large-scale statistics. So the question is, what happened at large scale when x and t are both large? One can do numerics. It's easy to implement that on a computer. Well, it's a bit of work, but it's perfectly feasible. It's a classical field theory that fluctuates, can discretize it and all that. And what you see is that when x and t are large, you find a nice profile that emerges, which is a function of the ratio x over t. So that suggests that there is some kind of Euler scaling. I mean, the theory itself is not scale variant, but somehow the evolution of this observable in space-time seems to develop a profile that depends on x over t. Now, so this is the typical Riemann problem of hydrodynamics, and it's a kind of a non-trivial problem for many-body system. You can also ask similar question for KdV and all that. So you can ask a similar question for the hydroid gas. Now, this is not a field theory, this is a gas of particles, but okay, you can ask a similar Riemann problem question where now you integrate over all positions the momentum of the particles with some distribution which are different if the particles are on the left or if the particles are on the right. And here you can actually ask something more general and ask about the distributions, which are generic functions of the momenta. So every momentum in the hard gas would have a certain distribution given by a function, W left and W right for the left and on the right. And what you can look at is different observable. And again, you can look at for instance, the density of the gas at position X. So consider delta function X minus Xi of t. Xi of t is the position of the ith rod as it evolves in time at time t. And again, you see, so the wiggly curve here are the numerical implementation, which I did actually quite some time ago. And you see some kind of profile developing, and essentially the profile, again, develops over time as a function of x over t. Eventually becomes a function of x over t. There's finite system effects here, but in the center will become a function of x over t. Now, in these two, there's kind of a black curve as well as a red one, and here there's the red curve as well as the wiggly blue one. And these are theoretical predictions for the exact profile that is developed over time in this calculation. So what is this exact profile? Well, it's this idea of hydrodynamics, very much related to soliton gas. Okay? So these Riemann problem people have studied in the context of soliton gases, but what I want to point out here is that it's a very general type of problem that you can study for a large variety of systems. And here the systems I'm looking at are field theory or gas of particles. And finally, for the last type of model that I was thinking about, the quantum gas, well, this is a completely different type of system. This is a quantum Hamiltonian, so many-body quantum Hamiltonian. So you'd have to calculate a wave function. And you can ask a similar problem, but like the Riemann problem, you can also ask something a bit more interesting, which is actually related to what people can do in experiment, which is the release of bumps. So for instance, you start with some initial state, which you can represent as a density matrix for this quantum Hamiltonian, many-body quantum Hamiltonian, in some temperature. And the quantum Hamiltonian, you put some external potential. So for instance, the initial potential can be of that form, and where it has two minima that will concentrate the particles, say, on the left and on the right. So there will be a lot of particles there, a lot of particles there, not too many particles there. So just some external chemical potential. And then you can do a potential quench. It's called it's essentially like a quantum quench that people have studied for quite some time, where you suddenly change the potential. You can do that in the experiment, actually. You have your potential using magnetic field. You suddenly turn the button and change the potential. And look at how this system evolved. And for instance, you can calculate, again, the density of particles at position X. So this formal quantum mechanical operator, which evolved with different evolution Hamiltonian, where, for instance, the potential is set to 0. So really the original integrable Lieb-Liniger model. And then you ask the question, what's that function of X? So you should see something. Now this is, in principle, you can formulate that, try to calculate. This is very hard to calculate. It's even very hard to simulate on the computer, because you'd have to simulate a many-body wave function, many-body quantum system. There are techniques that you can do using, that you can use, which are based on the Bethe-Ansatz. Of course, this Hamiltonian without the potential is integrable. So you can construct its eigenvalue its eigenstate by Bethe-Ansatz and all that. However, these techniques are rather limited because it's very hard to describe the original density matrix, the original state, using these Bethe-Ansatz eigenvalue, because the original state is for some Hamiltonian where there's external potential that breaks integrability. And so this is a certainly difficult problem to even simulate that. It is possible to simulate up to about 50 particles or so, while in the experiments, people can do up to 10,000 particles. So these are kind of evolution type of problems where you have an initial distribution, or statistical initial state, which is statistical, which is a distribution of field configuration, distribution of particle positions, and an evolution with an integrable equation, which can be a KdV equation, which can be a field theory, a quantum many-body system, or of any kind. Okay? So these are the problems that I like to think about and kind of propose the fact that there is a framework which allows you to access all of these models and to give explicit prediction for all of these special problems. So a Riemann problem and evolution from different initial density. Okay. Any questions about, by the way, if you have any questions anytime, please do not hesitate to stop me. So there's another type of problems actually that you can ask, which is also about large-scale statistics. So instead of evolution, you can take a state which is stationary and homogeneous. For instance, just take the Gibbs state. And here I take the example of the Singe-Gordon model, just because it's easy to write and one can even implement that on a computer without problem. So take exponential minus beta h, where h is the Hamiltonian of the Singe-Gordon model, classical Singe-Gordon, and integrate over phi and pi, and this is your state. And then look at correlation functions, dynamical correlation functions in that state. So the average of the product of two fields at different space-time point minus the product of average, connected correlation functions. Now, this is a extremely difficult problem. In fact, a problem that people have been looking into in the context of many-body quantum integrability for quite some time. Here, I'm writing it in the context of classical integrability. Okay? And there was no clear ways of calculating that until the advent of the hydrodynamic understanding of this problem. Now, this correlation functions has, well, there's a lot of features, but in particular, if you look at large space-time on a given ray, so x equals zeta t, what you will observe is that the correlation function decays with time. But it decays like 1/t with some kind of oscillation. You can observe that numerically, for instance. It decays 1/t with some oscillation. So if you multiply by t to take away the 1/t and then integrate over time, average over time to get rid of the oscillation, you get a nice finite curve, finite number that depend on zeta. You get a finite profile that depend on zeta. So correlation profile at large time. So here's the numerics. And the question is, can you predict? Can you give a prediction for a kind of correlation for this profile of correlation at large time? And the black curve is a prediction from the theory of generalized hydrodynamics, which I hope I'll get to there. Okay. So these are the type of problems, kind of a large-scale statistics problem, where you have an initial distribution which may be inhomogeneous or not, but which is statistical, which is fluctuating. And it is fluctuating, but at large scales, and you let it evolve in time, or you calculate correlation function if this doesn't evolve in time. And you want to predict what happened at large space-time. Okay. Any questions about that? So the idea is that there is a unique universal framework. This is a bit kind of maybe a bit pretentious, sorry about that, but at least for the four models that I have introduced, there is a framework that seems to work, where there's a lot of checks and everything seems to work. Okay? We call that generalized hydrodynamics. Okay? So for there are two types of problems that I described. The evolution problem from some initial inhomogeneous statistical distribution, like Riemann problem or like the potential bumps, and the correlation function problem. Okay, so let me start with the evolution problem. Okay, so I want to right away give you the equation. This is an equation that many of you know already from the context of soliton gas. And if you know GHG, then you've seen that as well. Okay, but what I want to say is that this equation that you might know from soliton gas is the right equation in all the situation that I have described. So for the KdV soliton gas, the Singe-Gordon model, two temperature initial value problem, even for the quantum, even the Lieb-Liniger gas and the hydroid gas. What is this equation? So it's a single kind of universal hydrodynamic equation. It's an equation for some kind of density of state. It's called density of state in the context of soliton gas or spectral density. It's a function of three variables, say a spectral variable theta and position and time. And so it's an equation that has the shape of a continuity equation. So it's essentially a hydrodynamic equation. At the Euler scale, this has the shape of a continuity equation. Now, let me say a little bit more, just to be kind of more precise, how we use this equation in the various models that I've described. But first, the KdV soliton gas, if I want to evaluate the average of the KdV field, all I have to do is take this particular function, integrate over theta multiplied by 4, and that should give you the average of the field as a function of x and t. So this is the evolution that will provide the correct space-time dependent of the average of the field. Now, I'll have to tell you about the initial condition as well. I'll come back to that a bit later. For now, I'm just thinking about the evolution of this function. So this function essentially represents the fluctuations, the initial statistical distribution, if you wish. And from that, you can calculate the averages. In the hydroid gas and Lieb-Liniger model, I was thinking about the density of particles at xt. In both cases, the example that I gave, well, you just have to integrate over theta, and that will predict the correct density function of xt. In a stage-Gordon model, I was thinking about this particular exponential of, I was talking about some exponential of the field. And here, for instance, I take I will look into, well, I looked at e to the 2g phi in particular in the example I gave. Well, this is a complicated function of rho, but it is known. So it's not just an integration over rho or something like that. It's a bit more complicated, but it's still known. So you can still calculate. It's known from integrability story. Okay. In stage-Gordon model. So this is an equation that describes physical quantities, and more generally, every local observable like u squared, u thirds, and e to the alpha phi, and any other observables in Lieb-Liniger model would be functional of this function, functional of rho. Okay. So what else is there in this equation? Well, there is this effective velocity. So this effective velocity, Vf, is also something that if you know soliton gas, you will have seen. And you will have seen an equation of this type. So it is a functional also of rho. It's a nonlinear function of rho, which is obtained by solving a linear integral equation. Right. I'll come to where this linear integral equation come from, okay? But basically that's what, now, in this linear integral equation, there are two quantities, there's the velocity and there's delta. So what is this? These two quantities are characteristics of the models that you're looking to. So for instance, I give you kind of the basic equation that one can find from the literature, for instance. If you take v equals 4 theta square and delta equals this particular function, that represents the KdV soliton gas. If you take v equals tan theta and this particular function, that represents the Gordon model, and v theta delta minus a, that's the hard-rod gas, and v equals theta delta, that particular function, that's the Lieb-Liniger model. All these models for statistical initial value problem, which are inhomogeneous, can all be studied by this single equation. You just have to put the right elements in it. Okay. This is a velocity, and this is a kind of a displacement, scattering displacement. So I'll come to this. Okay. So this looks like a very universal equation, a very strong thing. So the question is, where does it come from, and how do we understand it? Okay. So any questions about it? Sorry, there was a hair there.
Sorry,
okay,
can you say what theta means? What is theta?
Yes, sorry, I forgot this. Thank you, very good question, of course. So theta is a spectral parameter, and its exact meaning, actually I'll come to the more precise meaning when I explain the effective velocity. But it depends on the model, the exact meaning. And in fact, there is no unique meaning of theta. There is you can change your theta parameterization, and still the equation will be valid now. Okay? But it's kind of a spectral parameter, and it has a meaning in terms of asymptotic states. So it is like it kind of represents the momenta of asymptotic states, basically. But I come to this. I mean, that's kind of the heart of my talk, is actually to explain where this comes from, let's say, and then you see what theta means. Okay. Other questions?
Can I interject, Peter?
Yeah.
In case of NLS, it's integration along the accumulation curve for the poles, for example.
Indeed, indeed. So there's another thing which I didn't write, which is that integration here. That also is very much model dependent. And in all the cases that I'm thinking about, integration will be over the real. And the KdV is going to be over the positive real. And in the other one is on the full real line. In NLS, there's a similar thing that you can write. And then you have a non-trivial integration. In fact, there was a talk at the beginning where today where we see that there was a spectral parameter defined complex plane. And you have that as well. So there's a region, a manifold in general, where this theta or this alpha lives, and that's model dependent. Other questions?
Yeah, silly question. Just looking at Lieb-Liniger or Sand-Gordon, this delta, does it have a systematic connection to two-body scattering?
Yeah, exactly. So this is where it's exactly that. So in your talk, you talk about the two ways of seeing integrability, R matrix and scattering. Yeah. This is a scattering way. And delta is exactly related to the scattering two-body matrix. So in fact, delta is easy to calculate, I should say. So, deriving this equation in all this model is hard. As far as I understand, there is no rigorous derivation. The most rigorous is within the context of KdV soliton gas. And in the other cases, is very far. Well, in hard-rod gas it is, but in quantum it is very far from rigorous. But these quantities are easy to calculate from basic two-body process and dispersion relation. Other questions?
Thank you.
So, okay, so this is where I want to get to essentially. And so this is, I think, kind of makes the link from TdV to Lieb-Liniger to quantum, so from soliton gas to quantum gases. There is a seemingly universal framework that seems to work for that of model. Yeah, okay, so what's the basic idea behind all of that? Well, the basic idea behind all of that is hydrodynamics. Anyway, there are many ways of understanding the basic idea, but that's the way that I like the most, because it seems to be very fundamental and kind of it brings you very far, in my opinion. And what's this way? Well, if you have an any-body system, like a gas of particles, like a dynamical system, like a KdV equation or whatever, you can imagine that there's a statistical initial distribution now which is homogeneous, and you evolve it in time. So what you can imagine or hope or maybe eventually prove is that you have some kind of local ergodicity fluctuation. In fact, ergodicity is a word perhaps that is a bit too strong for what I want to say. There was a talk this morning about ergodicity and lack of ergodicity in integrable models, for instance. But what I mean is basically that locally, you should think you think that your system will have time to maximize entropy in some way. So, but the way it maximizes entropy will be different where you look locally. So here it looks like there's a lot of particle, here it looks like there is less. But if you just look there in this mesoscopic scale, it will look like it's homogeneous and stationary. So for large distance compared to microscopic, but small compared to macroscopic, for these distances, it looks pretty much homogeneous. And similarly in time, for these times, it looks pretty much stationary. This is kind of state that you have. So you want to describe your model by taking homogeneous stationary states, but that depends on space-time. That's the basic hydrodynamics. Let me put some equations to that. So how you do that? Well, the starting point of hydrodynamics is the set of conservation laws. So you've got to know what are the conservation laws allowed by your model. Now, what conservation law? Well, local conservation laws, for instance, energy, momentum, particles. If you have an integral models where you have the higher conserved quantities, for instance. Okay, so these are conservation laws. And what you do, the other thing that you need to know are the homogeneous stationary state that maximize entropy, which is purely from physical principle, right? It's not a derivation, but it's physical principle of hydrodynamics. So you have to know what these states are, and according to the old stuff of 20th century, Gibbs, or more generally the Janes states, are of the form exponential minus sum of whatever parameters, some kind of generalized inverse temperature associated with every conserved quantity. In the modern parlance, this is called the generalized Gibbs symbol in integrable models. In the old time, this was just called the Gibbs symbol, where you had just the Hamiltonian and perhaps the number of particles. Okay. And what you do with that, well, you say, okay, let me make the Hydro approximation. That's the picture I had in the previous slide. The Hydro approximation is that every local observable at xt evolve in time, in such a way that you've had time to kind of maximize entropy locally, can be described locally as an average is in one of these maximal entropy states. But the parameters of this maximal entropy state depends on space-time now. So different place in space-time, you've reached a different maximal entropy state. That's the hydrodynamic approximation. So this is the thing that is actually hard to prove. And in non-trivial interacting models, there are very few mathematical proof of that. But it's an approximation you can make. And once you make this approximation, you can deduce the dynamics on these beta simply by writing the conservation laws for the averages within these maximal entropy states. So you write the conservation laws at the mesoscopic level. Okay? And these are the hydrodynamic equations. Okay? So this is the general form of the Euler scale hydrodynamic equation for any many-body system that you have. So all you have to know are the conservation laws and these maximal entropy states. Okay? And in these equations, the dynamical variables are these betas, the inverse temperatures, essentially. In fact, since these Qs are just average respect to betas, and there's as many betas as there are Qs, you can inverse this relation there. You can think of your dynamical variable as being the Qs themselves. You should convert the relation. And so this is a reduction of the effective dynamical variable for your many-body system. You don't have to take care of all the trajectories of all your particles. All you have to remember is these functions of xt, so the average conserved densities as function of x and t. So it's a reduction of number of degrees of freedom. is hydrodynamic reduction that is supposed to occur at very large space-time scales, when things vary at very large space-time scale, for instance. Okay. Any questions about this? So, of course, you can, since the currents themselves are a function of the betas, and the betas can be written in terms of q's, you can invert that, and you can write this in the quasi-linear form. So you can write the currents as function of the q's, and then take the derivative, and then you have the quasi-linear form of this Euler scale hydrodynamic equation. Okay? And in this quasi-linear form, there's a flux Jacobian which is involved. The flux Jacobian is just the derivative of the current with respect to the densities. You know, the average currents in maximal entropy states with respect to average density in maximal entropy state, where there's a D missing there. And this flux Jacobian has a very interesting physical meaning because its spectrum is real according to general statistical mechanics principles. It can be shown from the statistical mechanics that this should be real. And is identified with the set of hydrodynamic velocities which are allowed by this many-body system. So if you perturb a bit the system, there's kind of sound wave coming out at different velocities. And these velocities are not linear, but in the spectrum of this A matrix, the flux Jacobian. So this is kind of the basic hydrodynamics. And the point is just to apply this basic hydrodynamics for the different dynamical system that I had at the beginning. Okay? So KdV as a dynamical system, so integrable turbulence as a dynamical system with a fluctuating initial condition, I can apply hydrodynamic on that. So apply hydro on KdV itself and on Singe-Gordon and etc. etc. Okay? So two things I want to say here about this hydro. So one thing is that, okay, so what is this hydro approximation? Well, it is hard to control the hydro approximation, but if it does work, it will work in the following sense. It will work in the sense of the Euler scaling limit. So if you have an initial state which is inhomogeneous, and suppose it is inhomogeneous on some large length scale, lambda, and you evaluate an average of a local observable at large space-time position lambda x, lambda t, take lambda very large. Well, if this Euler hydro is going to work, the limit should depend on these beta of xt, and these beta will satisfy the hydrodynamic equation. So that's the meaning of Euler hydrodynamic equation, really. Now, there's a lot of subtleties in Euler hydrodynamics, especially with development of shocks and all that, but notwithstanding these subtleties, that will be the meaning. The other thing that I would like to say, which is very important, is that, so, because for hydrodynamics, we are used to the notion of perhaps, well, Boltzmann introduced the notion of molecular chaos, for instance, right? You want things to kind of be ergodic locally and thermalize and all that. But it is important to realize that it is not necessary for the system to be chaotic, or or to, in fact, to have, so the system does not need to have very, very stringent properties, ergodicity properties, for this to work. So even if the system is not chaotic, still there is a notion of hydrodynamics. What's the difference? Well, the difference is that the manifold, general system manifold of maximal entropy states will be very different if the system is chaotic or not. So of course, this is natural because the maximal entropy state is controlled by the constant of charges. If you have just few constant of charges, well, you have a finite dimensional manifold, but if you have a lot, you're going to have an infinite dimensional manifold. And so you have much less reduction of degrees of freedom when the system is integrable, for instance, but you still have a reduction, and there is still a hydrodynamic notion. Okay, so that's the idea. It's a very general set of ideas, very general notion that can be applied quite generally. So the non-trivial bit, the tricky bit here is to find, well, one is to find the set of maximal entropy states to characterize it properly. And once you have that, the other tricky bit is to calculate the currents as function of the density in order to have your hydro equation. So these are the two things that are needed in order to use that for a many-body system. Okay. So let me, so in integrable system, it's possible to do that thanks to the notion of scattering. So I was saying, so Vincent was in his talk, was talking about the different ways of seeing integrable models. One of the ways is as factorized scattering. So here you think of your many-body system, suppose if it's a gas, then you look at very far in the past and very far in the future. If the system is on the line and beyond where the energy is, it's a vacuum, what you will see is freely propagating particles. fact, the same holds for the KdV equation. If you have a region of space which is finite, large but finite, where there's non-zero indigeneity, and you let it evolve in time, eventually that will decompose into its independent scattering components, for instance, the solitons. Okay. So you have scattering components, and it turns out in integrable models, in all the models, for instance, that I've talked about, that the scattering is factorizable and preserves all the momenta. So the set of momenta coming in is the same as the set of momenta coming out. So you see here my theta are kind of alias for momenta, if you wish. And the total scattering matrix, which can be a quantum or classical scattering matrix, factorizes into a product of two-body scattering matrices. So that's basic of integrable system. Okay. Now, with this, let me kind of discuss how to apply all these general ideas in the models that I've talked about. In fact, the easiest one is a hard rod gas. So let me develop the hydrodynamics of the hard rod gas. Yeah. So, okay, so here the hard rod gas is just a gas of particles that move in 1D at given velocities, and when they interact with each other, they just exchange their momenta. So it's kind of just elastic collision. Okay. So as a consequence, so this is a typical kind of a two-body process. Here's my two-body process. In fact, the whole evolution is just a set of two-body processes, because it's very unlikely that three rods will suddenly come to the same point together. Okay. So this is really explicitly dynamically separated into two-body processes as you time evolve. It's like the simplest possible situation. Okay. And here's a two-body process where you have a momentum there that is being changed to the rod, and that continues there. So you can construct a lot of conserved quantities. Actually, you can construct a continuum of extensive conserved quantities. You just construct the density, which looks at if there's a particle at position x and if this particle has a momentum theta. Momentum equals velocity, so they just unit mass. Okay. So this is a function of x and theta, and these are continuous variable. Sorry, were there questions?
There is a question in the chat.
Yeah.
So what if there exist more conserved quantities than are known or used in the formulation? Is it about what is true for the system or about what is known about the system that is important for formulating the hydrodynamics?
So thank you for this question. This is really excellent question. And this is actually one of the trickiest points, in fact, of this whole construction, which I'm kind of putting a bit under the carpet here. You have to know, you do have to know the complete set of conserved quantities. Otherwise, it will not work. And this was one of the things that didn't work at the beginning in the context of quantum thermalization of integrable system, that people didn't know the complete set of conserved quantities. Okay. So you do have to know the complete set, and it may be difficult. And in general, yeah, you might be missing some. But so I say that. On the other hand, this complete set may divide itself into separate subsets which do not interact with each other. So you have to know a complete separated subset, let's say, and that will work. I don't know exactly how to explain that fully because I don't have a really good understanding, but an example, for instance, is the soliton gas. Solitons are not the only asymptotic, well, okay, I'm going to explain that in the context of soliton gas in the next slide. But so an example is soliton gas where you don't have the complete set of conserved quantities in your formulation of the initial statistical distribution, but it doesn't matter. It is sufficient for the hydrodynamics. You have a complete enough set. So I don't have a very good answer, but there is this notion of it should be complete enough, but it's not, maybe not necessary to have the full thing. So your initial state might lie within a subset, of kind of a eternal minus beta q, which is a subset of the q's, and that might be sufficient, or it might not. So it's a bit tricky. But yeah, so it's a good question, and I don't have a full answer. So we have an understanding in the model that I'm describing there. There's some kind of understanding, but not the full answer in general. Other questions? Okay, so here the hard-rod gas, I mean, this is, nothing tells me that this is a complete set, of course. It's just a set that I construct. But it seems to be complete enough. I don't know how to prove this is complete, but it seems to be relatively complete. What it says is just counts the, each momentum in this interaction, in this process is preserved throughout time. And so, you can think of each momentum as being itself kind of a conserved quantity. So you can just look at C at x if there's a momentum pi. When you integrate over x, you just look overall if there's a momentum, a momentum theta. And if it's there at time 0, it is there at all time. As simple as that. This is conserved. Okay. And then you can just construct your maximal entropy states just by now not summing over beta I, but integrating over all this continuum of conserved quantities with some function. And all it does is really putting a weight for the various momenta. So it's a function of momentum, and you just put the weight exponential minus sum over I W of pi. So for every particle, you weight the momentum according to this function of W. So now there's a one function family of maximal entropy states. So it's a big state. It's a big space of state. Okay, but still, one can try to use hydrodynamics. So if you want to use hydrodynamics, okay, what do? Well, you calculate the conserved densities. This can be calculated in this model, but as a function of this W. But it doesn't matter what it looks like exactly. It's just some function of theta. Okay, so this is the average of that quantity within these states. Okay, it's just some function of theta. But what we'd like to know is the current as a function of this. Okay? And here comes this collision rates ansatz, which allows you to calculate the current. It's very simple for the hard-rod model. You look at the two-body scattering process, and what you realize is that in a two-body scattering process, the particle that carries a certain momentum essentially jumps. The momentum carrier jumps by a distance a whenever it hits another particle. And so the idea of this collision rates ansatz is simply to multiply this rho, which is the density of momentum theta, by a velocity. And this velocity is essentially the velocity you would obtain by looking at all these collisions, and by seeing, so overall maybe I should put a little drawing there. So you have, it will do something like that, collide, and do something like that, collide, collide, and collide, etc. And overall, there will be a total displacement that corresponds to a certain velocity. And that's all you have to know. You just have to know that velocity. This is called the effective velocity. And this formula implements the calculation of the effective velocity. What it is kind of the linear bit, the displacement, plus the sum of all the jumps that have occurred due to the interaction with the particles. Now, some of the jumps will depend on how many particles there is of different velocity alpha, and depends on the jump that you do. Now here, for the hard-rod scattering, the jump that you do is -8. So the two-body scattering is described by this delta equals -8. Okay? And the difference of velocity is kind of just a probability that the particle with velocity theta hit with rapidity theta, with parameter with bare velocity theta, hit a particle with bare velocity alpha. So overall, they will displace themselves as VF theta and VF alpha. And so this difference will tell you if they will eventually meet or not. If the VF are equals, they will never meet. If they are different, they will meet at some point, and that takes into account as well of the direction where the jump occurs, right or left. So this is an equation, that's the integral linear equation that I had written previously. And it is just a matter of evaluating the total displacement, the effective velocity obtained by total displacement of a test rod within a gas of other rods. Total displacement is due to the free displacement and the jumps. It's collision rate ansatz, and then you just take current equals this. What you obtain is the hydrodynamic equation, which is this one, the one that I had written previously. And this hydrodynamic equation actually has been proven rigorously in 1982 by these people using different techniques. So not using this kind of naive technique that I'm talking about, using different techniques. So this is actually a correct hydrodynamic equation that occurs at large scales with initial statistical distribution. Okay? And follows from this collision rate ansatz. Questions about this? So you can then look at the other models, okay, the KdV soliton gas. Well, so this argument of the collision rate ansatz was made already by NTL some time ago. And here, basically, what you think of, well, okay, you have again your conserved densities situation. You want to calculate the maximum entropy states, but here we can restrict ourselves, for instance, to maximal entropy states, which are only described by solitons. What does it mean? It means that you have some region of non-zero energy density, say of length L, and you ask for this region to decompose asymptotically in large time into, say, n solitons. So this is a specific, form of the n soliton, right? Usual form of solitons in the KdV equation. And that in particular tells you the meaning of theta. Theta characterizes the soliton, characterizes its velocity, which in KdV also, characterizes its amplitude and all that, okay? So, so you ask for configurations in finite L, which decompose into n soliton. And then you take the limit when L and n are large. That's your maximum entropy state. It's kind of a large state on a large space, which represents the mesoscopic scale, okay, with fixed density n over L. So what you obtain, you can describe then the state using a density of solitons. That's the density of state in the context of soliton gas, which can be seen simply as taking the number of solitons which have theta between, say, theta1 and theta2 and divide by L, and that will, give rise to the integration of this density from theta1 to theta2. Okay. Now, so essentially what you do there, you forget about the x0, which is this little displacement. You make them random, so there's kind of a dephasing occurring, and the only thing that you remember that you use to characterize the states are the thetas, which are the velocities or momenta of the solitons. Very similar to the hard rod gas, where we had the momenta. Okay? So this rho is similar meaning. And then you want to do, so there's a relation between the conserved densities and these rho's. So it's a simple relation. So all these conserved density, which are obtained using the KdV field, can be expressed as integration over density of solitons. Qi will be a power of theta I. Okay? And there's some constant there that one has to calculate, which in principle can be calculated. But what about the average currents? Well, again, there is a collision rates on that. So here, if you look at the two soliton scattering, so we know from theories of integral models that two soliton scattering, something non-trivial happen at the moment of soliton scattering, and then the soliton come out of this kind of unaffected and looking like nice solitons with the same velocities, except they have shifted a little bit. So there's a little bit of a soliton scattering shift, and this can be calculated in KdV, and is that formula. In my convention, delta here is a negative, so a shift forward corresponds to a negative number. Okay. So there is a two-body scattering shift. So that's the question that Vincent was asking. So what was that? Well, the delta that's there is exactly the two-body scattering shift of the soliton gas. And then you can do again a collision rates ansatz for this soliton gas. Now, this collision rate ansatz is the same idea. You imagine that you have a lot of solitons that scatter with each other and shift and shift and shift, and you accumulate out the shift that gives you a velocity. However, here, this is not very well justified, because this is not true when you have a dense soliton gas that you can identify each solitons independently. So this is kind of a naive picture. Nevertheless, you can do this naive picture and propose this value for the current. Okay. Any questions about this? So once you have that, okay, so here's a little picture that I take from papers of genetics, where you see a soliton propagating within a sea of other solitons. And the red one is the numerical soliton that propagates within that sea. And the dotted one is the one where there would be no sea at all. You see the red one went a bit faster than the dotted one. And that's because there's a different effective velocity. That's because of the accumulation of all the shifts. It's something you can really see numerically. Okay. So, okay, from this, you would write this equation, and it turns out that this is the right equation. It was derived in completely different ways, not by this kind of a collision rate ansatz, but a posteriori interpreted as being an equation that follows the collision rate ansatz. So really, you think of solitons as if you have a gas of solitons which are well identified and which scatter and jump kind of throughout the gas. Okay. So this is the correct, this is the usual soliton gas equation with collision rate and that. And you can do the same thing for the Lieb-Liniger model. Now, the Lieb-Liniger model is a quantum model. So there's an additional complexity that not only the wave function is complicated and all that, but it's a quantum model, so you don't have well-defined trajectories. Where there's still the notion of scattering states, where you have momenta that emerges at large time in your scattering state. So these theta then are asymptotic momenta of scattering state. So again, you imagine you have a large finite region and you let it expand, and then you have various momenta, and you characterize your state, your statistical ensemble, by a distribution of these asymptotic momenta. So that's the general idea. And again, the conserved densities can be written, they're a bit more complicated to write, but they all have the form of theta to the I rho p. And in general, the mixed state, which are some of these QI, one can do a Bethe-Ansatz calculation of this, and they are characterized by this density of asymptotic state. So this in Bethe-Ansatz is essentially the density of a Bethe root, which is interpreted as density of asymptotic states. But then, of course, the collision rate ansatz for the currents is a bit more complicated. You can still do it by using a semi-classical picture. So here in Lieb-Liniger, there is a known two-body scattering. It's a quantum model, so the two-body scattering gives rise to a quantum phase. So you can explicitly work it out by a simple few-line calculations. What is this phase in the scattering problem of the Lieb-Liniger model? Okay. And by semi-classical analysis, if you have wave packet of Lieb-Liniger waves, essentially scattering with each other, what you would expect is that the derivative with respect to theta, which is like here the momentum, of this of the log of this two-body scattering phase, that would correspond to the displacement of the semi-classical wave packet. If you take that semi-classical picture naively and put it in the expression of the currents again, so the currents are, VF times rho, you replace rho by VF times rho, you get an equation, so which is the hydrodynamic equation which I wrote, and it turns out that this is the correct equation for the emergent hydrodynamics there too. Now in the quantum case, this expression was derived in very different ways, not by this semi-classical analysis of collision rates, but by using the first derivation we did it was by using the thermodynamic Bethe-Ansatz for the quantum Singe-Gordon field theory, where rho is the Bethe root density by using QFT crossing symmetry to identify currents with densities, and then by taking the non-relativistic limit. So a set of steps which are pretty complicated. But where we got exactly this expression for the currents, which can be a posteriori interpreted in terms of collision rates and that. There are also other derivations that have been obtained later on. And so these equations were proposed after, of course, the development of soliton gas, although at that time we didn't know. They were proposed for Bethe-Ansatz integral quantum systems as a hydrodynamic for Bethe-Ansatz integrable quantum systems in these two papers. So overall then, okay, for the Singe-Gordon model, there's also a notion of delta. And now in this case, it's going to be, it is interpreted as a shift induced not by soliton scattering, but by phonon scattering. So the Singe-Gordon model emits phonon excitation, so these waves, radiative wave excitation, and they also are subject to a scattering shift. And it turns out that the currents are correctly obtained by using scattering shift of phonons. Okay, so just to recap a little bit. So if you do conventional hydrodynamics, it's a very simple set of equations. Conventional hydrodynamics, you have a conservation of mass and Euler equation. Well, for many body integrable systems, this is incorrect. You have to replace this by an infinite set of conservation laws for all the conserved quantities. And it turns out you can evaluate the currents in these infinite set of conservation laws using a collision rate for all models, classical and quantum, it turns out. And what you get is a nonlinear integral differential continuity equation for a spectral density. And the spectral density is basically a density of asymptotic states that represents your local fluid cells, the statistic of your local fluid cells. And it's the same equation for a wide range of models. Any questions about this? So if I just wanted to kind of show, so time is short, but the fact that this doesn't work and that works has actually been observed in experiments. I told you that the Lieb-Liniger model can be experimentally implemented using cold atom gases. So there is one way. This is a picture from the Institut d'Optique, Isabelle Bouchoul, which is the leader of this lab. This is one way of constructing these quasi-one-dimensional systems by using cold rubidium atomic gases, which are confined using magnetic field. So you have kind of a magnetic field that confines them into 1D, and some other magnetic field, produced by these line of currents there that produce some kind of external potential that allows you to kind of start with some initial density of particle, as you wish. And so what you do, you start with some external potential, you kind of cool down your atoms and they are distributed in a certain fashion. Then you take away the potential, you change it in some way and let the whole thing evolve and try to, and in this experiment is quite amazing because it can actually take pictures of these atoms. So there are pixels, and in the pixels is about 10 atoms or so. And so you have pixels of the density of particles. And these are the curves that one obtains. So the wiggly curve is the experimental one. The dotted one is the conventional hydrodynamics, if you forget about all the conserved charges. And the kind of full one is the one from generalized hydrodynamics, if you take into account the conserved charges and the collision rates on that and all that stuff. And it seems to be working extremely well, because this is an experiment. There's a lot of stuff that can happen in the experiment, but that does reproduce the experimental curve very well. So in GHD, one has, so there's quite a lot of work that have been done to go a bit further from this earlier hydrodynamic equation. In particular, it is known how to introduce external forces. So what I mean here is, suppose that I have a potential like that initially, that describes my evolution of my initial state, and I suddenly change this to a different shape. A different shape, there's still a potential that will put forces on the atoms. And so like the V evolution is non-zero, it's something else. So whatever shape it is. Well, there's a way of modifying this equation by introducing some kind of effective acceleration that will account for the different shape of potential. In fact, that account for different shape of any external coupling to any conserved charges, or there's even generalization to kind of the change of the interaction parameter itself. So there's a more general equation that has been looked at in the quantum case, and that probably works as well for KDV soliton gas, although this has not been looked at yet. But in principle, this is very general. There's also possibility of introducing diffusion. Now, this is based on the hydrodynamic point of view of this. So when you do hydrodynamics, the leading order is the earlier scale, but then you have sub-leading order, which are higher derivative terms. And we know, it's conjectural, but calculated in various ways, we know how to modify, how to add a second derivative term. See, you have two derivatives there, dx, dx. A second derivative term that should account for diffusion. What kind of diffusion is this? It's an integrable model, but diffusion is a bit like I was saying this morning, that when you think in terms of kind of soliton scatterings, well, they jump a bit around that produce an effective velocity, but these jumps are kind of random. It's a bit of a random walk there. It's a very naive picture, but it's exactly what's happening certainly in the hard-rod gas. And it's a kind of a extension of the collision rate ansatz to the randomness of these jumps. And so that gives some kind of diffusive spreading. And it turns out that this diffusive spreading can be recast into a very particular integral operators that is a nonlinear functional of rho, and that has an explicit expression. So there's an explicit way of writing this operator. Very complicated, but still explicit. And so you have an equation that includes diffusion, and yeah, we've done numerics also with that, and seen that in for instance, in the Riemann problem of quantum spin chains, that indeed improves agreement with the numerics. So diffusion is the correct expression, correction. Any questions about it? So I think my time is up. Yeah, Constance, time is up, or yeah, probably, right?
Yes, but if you want, I think that we can give you some more minutes.
Yeah, so I don't want to say too much more. It's just that there's a lot of things that have been done both in the quantum gases and the KDV gases. There was one thing that I did at the beginning. It was the thing about correlation functions. I said, you can also calculate correlation functions. Well, it turns out that there is a general theory for calculating correlation functions in hydrodynamics, and it's the theory of hydrodynamic projections, or Boltzmann-Gibbs principle. So if you think of hydrodynamics in a completely general fashion, there is this notion of if you calculate dynamical correlation functions between two operators, what you have to do to calculate is basically project these operators or these observables onto the long-lived waves, propagate the long-lived waves, and then project back into the observable that you want as space-time point xt. There's an explicit mathematical formula for this picture. And it turns out that in generalized hydrodynamics, one can write this rather explicitly. So this is the expression. Okay? So this is a two-point function. You do a Fourier transform, and you take the Euler scaling limit when t is large, k is small, and kt is fixed. K is like the wave number. So what you get is certain functions that represent the projection of these observable onto the long-lived modes, which can be identified with the asymptotic states theta, and a propagation which is controlled by the effective velocity. There's also the density of state, and there's a particular function f, which I haven't explained, which encodes the statistics of the long-lived modes. So either they are fermionic, bosonic, they're particles. So this encodes the statistics, so quantum or classical. So this knows about quantum and classical within that function. So these v can be calculated if you know the average observable into maximum entropy states. You can write this average, the derivative of this average, the susceptibility with respect to external temperatures in terms of in a certain way that extract this projection essentially. So using these formulas, we have computed everything necessary in the Gordon model and compared with the numerics, and that works very well. And so and again, this is something that can be done also in context of soliton gases or in quantum context in principle. So this is kind of the general universal theory that allows you to calculate these correlation functions. It's not been done yet for soliton gases, for instance, KDV soliton gas. And that's what I wanted to say. So there's a lot of things that one can do with GHD. It's been applied to a lot of models until now. Some rigorously, I mean, of course, much before the advent of GHD, like in the classical hard-rod gas, and almost rigorously in soliton gases, and some less rigorously, but kind of going beyond like in quantum models and classical field theory of all type. There's a lot of structure in this GHD equation. There's actually an integral equation solution to the GHD equation itself. There's a solution by characteristics to the GHD equation themselves, in fact, that you can write down. There's some integrability structure that's been worked out by people, especially in the context of soliton gases. There's various numerical techniques. There's also a MATLAB package actually that has been written to solve the GHD equation, including the soliton gas equation, by the way. So it's very conveniently written. Where you can solve this equation quite efficiently. And there's a lot of stuff that had been calculated, such as full counting statistic for transport. Integrability breaking has been looked at a little bit. There's quite a lot to do, and a lot of papers, and I encourage you to look, well, okay, in particular, my Jesus lecture notes on that. Herbert has a nice overview of GHD in the classical TODA model. It's very instructive if you know a lot about classical integrability. NADS has a nice soliton gas overview, and there's a JSTAT special issue on emergent hydro and the many body systems, where there will be a lot about GHD. And I finish with these kind of small open problems. Thank you for your attention.
Thank you very much for your great talk. So I guess we can open the floor for questions and discussion. So anybody got any questions?
Yes.
Can I ask a question? Oh, go ahead.
I think you mentioned all along I've been puzzled by the fact that you seem to say that whether it's classical or quantum, it doesn't matter for the formalism. But towards the end, you mentioned this function f.
Yeah.
So could you say a bit more, because that might answer my puzzlement.
Yeah, thanks. Yeah, thanks, Vincent, for asking
that it's either Fermi-Dirac or Bose-Einstein, but what is it if it's a classical system?
Yeah, thanks a lot, Vincent, for asking the question, by the way, because I didn't have time to go through that. So it's really great that you're asking that, which allows me to go back to and properly explain the thing. Indeed, so the GHD equation itself apparently does not know about, so this one, for instance, does not know about quantum classical, apparently, right? So you do a completely semi-classical picture, and apparently it seems to be wrong, correct, right? Even if the calculation of this VF and all that is obtained from quantum beta, and that's in the end, it looks like it's all classical. Okay? I don't know exactly why it works so well in this equation when just semi-classically. I don't know, right? Because the calculation, of course, in quantum model was done from beta and that's now that. It turns out this semi-classical picture works. I don't know why, but in any case, what I can say is that you will start observing quantumness when you go beyond the earlier Hydro equation. So when you go, so I go there, when you start doing thermodynamics and fluctuations, including correlations. Yeah. So here is the thermodynamic Bethe ansatz, and here is, I think, the answer to your question. So the thermodynamics, what it is, well, basically you have, for instance, in the hydroid gas, there was a function that was determining the weight for every momentum, right?
Yeah.
So you want to relate this function to the average densities, or to rho, say. Okay. And for that, well, basically you use the free energy. So you calculate the free energy, and the free energy is the generating function for the average conserved densities. Okay. And this is this is, as you know very well, so this is the standard thermodynamic Bethe ansatz, which allows you to calculate the free energy and all that. But it turns out that this standard thermodynamic Bethe ansatz can be extended a little bit to encode all of these models, so classical, quantum, and all of that, turns out. And the general structure appears to be as follows. This is, of course, not derived in general, but kind of from observation in various models and extracting what it looks like it's correct. Okay. So you have some dressed weight. This is the Zamoyski pseudo energy. And there's the bare weight, which is what is in the trace conventional minus beta h and all that. And then this bare weight is modified by a certain function, which includes the scattering, the two-body scattering phase, which can be understood as some kind of a change of metric in space. It's like when you do the jumps, you either add space or subtract space from the point of view of the particles. And then there's the function of this pseudo energy, and that function encodes the statistics. So if your model, if your asymptotic particles have a Fermi-Dirac distribution, like in the Lieb-Liniger case is the case, because the asymptotic particles are fermions in some construction, then you'd have this function for the free energy function. That's the standard TBA of Yang and Yang for Lieb-Liniger. If you have a classical model, say the hydroid gas, where you have particles, then you put the Maxwell-Boltzmann distribution. And if you have Singe-Gordon, in the Singe-Gordon thing that we're looking at, we had radiative modes. It's not particles, it's kind of waves, that emanates. And these radiative modes, they are in 1 over epsilon for their free energy function. And the 1 over epsilon, the fact that there is there may be a divergence, epsilon equals 0, is related to the black body radiation, kind of a UV catastrophe of classical field theory. Anyway, so there's 1 over epsilon. So you encode the statistic there within that function, as free energy function, and that tells you exactly the full free energy, and from that you can in principle calculate a correlation function, and then the f that I had there is just something calculated in terms of this capital F. So it's some function of theta, that depends on the statistics. It depends on epsilon, that depends on the state, that depends on statistics and all that. And that's the thing you have to put in here to have the correlation function. So correlation functions know about the statistics of the model, but not the Euler equation itself. So there you start seeing the quantumness.
Right, okay. Thank you. Thank you.
Can I please ask a question? Can you comment the previous slide that you were showing with free energy and stuff? Yeah. For the case of KdV soliton gas.
So I would like to comment, but I don't know. Thanks for the question. So, of course, with Gennady and Thibaut Bonneman, we actually are right now looking into that, and I don't know the answer. I'm sorry about that. So my intuition would be that for the KdV soliton gas, because these are solitons which intuitively kind of behave like particles, I would put the Maxwell-Boltzmann distribution. But I don't know, maybe there's some condition of not being together and it's Fermi or something, I don't know. Or maybe it's a different function altogether. We're investigating this now. Thank you for the question.
Thank you.
Any other question? I see there is a
question. Can I ask a question?
Yeah, sure, go ahead.
Okay, so just for me to better understand what is state of the art in your work. So basically, please correct me if I'm wrong. My understanding that you assume this pairwise collision, and it's somewhat empirical approximation, not exact, right? Then question, can you compare this with some microscopic dynamics? I don't know, hard rods or solitons. Is that done? Any comparison with generalized hydrodynamics or not?
Yeah, so there's been a lot of comparison with macroscopic dynamics. There's still a lot to do, however. But with comparison with hard rod, there's a lot of work that has been done. So in fact, for the hard rod models, I should say, so I think I said at some point, these GHD equations for hard rod, they were derived, they were proven rigorously already in 1982. And the hard rods, and these equations were even written earlier on by Spohn and other in the 70s. So this is known for a long time for the hard rod. So that works well. And we've gone a bit further with correlations and all that, and compared with numerical simulation of hard rods, and everything works. The most non-trivial, of course, is the quantum case. Quantum case is absolutely non-trivial. Now, the derivation is the collision rate on that. It's a nice interpretation. There are various derivations actually for the exact currents in the quantum case, which are based on Bethe ansatz, which are a bit stronger than the naive type of interpretation that I have given. So these are derivation of average currents, but it's not, of course, derivation of the actual Hydro equation itself. The Hydro equation is always a Hydro approximation in the quantum case. Okay? So, but there are some good derivation, and then there are some comparison with numerics, and we've done comparison with. We've applied all this, for instance, in the XXZ quantum chain, and with that you can do quite good TDMRG numerics. And we've done well. So the original work by the other group that was writing, show you the reference. Yeah, by the group of Bertini, Colorado, and Fagoti, they looked at the XXZ quantum spin chain. They implemented this equation kind of numerically and compared with simulation of XXZ for the Riemann problem, in particular, the domain wall. And they looked at various quantities, for instance, the density of energy. And that worked very well. So the comparison with simulation seems to work very well. And we have extended this comparison to the addition of diffusion term, and then the agreement works even better. So it looks like the hydrodynamics is working very well. And other cases that have been done, so there's a lot of, so in my conclusion, there was, sorry, a lot of models have been extended.
Diffusion term is that, I kind of miss, do you still need diffusion, for example, for integrable case?
So in general, the correct equation, the full equation, okay, is really, sorry, a lot of stuff. So the full equation is this one for integrable case. So this is really GHD for hydrodynamics of integrable systems. Okay? So there is the Euler part and the diffusive part, but this term is at least at large time when things are very smooth in space, very much subdominant. So you can neglect it, but in principle, it's always there. So when you compare with numerics, supposedly your comparison will be better if you add this term than if you don't. And that we've done, and add the term, and for the Riemann problem, the argument is better in XXZ quantum chain. So the diffusion is always there. Well, it's except if your model is free. If it's a free particle model, it's integrable, but really free, so no scattering phase, then diffusion is 0. But if there is a non-trivial scattering phase, diffusion is non-zero and it's always there. So in principle, it is there also for the KdV soliton gas, for instance. And I think that's one of the interesting things. Can you, in KdV soliton gas, one has much more control over the derivation of this equation, for instance, by modulation techniques, which at least have not been developed in quantum case. And so can one derive that from modulation techniques, KdV soliton gas, and can one check that this works now? That this is probably one of the most important problems to go beyond. Yeah.
Well, can I ask, or maybe add to kind of simultaneous to this discussion? Benjamin, you mentioned, well, you're in this whole problem, you have several spatio-temporal scales, microscopic, mesoscopic, and macroscopic.
Yeah.
And you don't introduce this explicitly. So your X is, well, different compared, well, for kind of different stages of the consideration.
Yeah.
And this is a question and maybe comment. When you look at the at your diffusion equation conservation equation with diffusion, it involves maybe, and this is a question, a different scale compared to kind of conservative generalized hydrodynamics, so to say.
Yes. Yes.
That's I think this is the reason, the difference. So it's not artificially introduced terms.
Yeah, it's so indeed correct. So for instance, if we do the Riemann problem, you start, say, with density that look like that, and then you evolve, and then if you just do Euler scale, you will see something that perhaps look like this and look like this and all that. If you add diffusion, well, at the beginning, because you have large spatial derivatives, the second derivative term will be relatively important, and then you're going to have a modification, something like that. I don't know if I have the right modification, but then eventually you will see no difference because the spatial derivatives are very small. So as you say, indeed, it's a question of scale.
Yep.
So here is, I don't introduce the explicit scale, but it's always there. And what we had observed is, indeed, if you do the kind of numerics, the exact numerics, like TDMRG, you observe something that agrees very much. In fact, we didn't see a lot of difference from early time with a diffusive solution. Yeah.
Okay.
Thanks.
Thank you.
Any other question? So if there are no other formal questions, I guess we can go to the more informal part of the meeting today, which is the discussion following Ben's talk and all the talk we had today. So I think we can stop recording and streaming.